So as I was saying, first I did this so that you can kind of understand what removable discontinuity is. It's just where there's simply a hole. So now let's move on to a real life example. Well, to like an example. So we have the function f of x is equal to x plus 2 over x squared minus 4. And we are given that f is negative 2. We are given that f is negative 2. So x would be negative 2. So what do? You plug in negative 2 for x. So let's go ahead and do that. So we would get negative 2 plus 2 is negative 2 squared minus 4. So negative 2 plus 2 equals 0. Negative 2 to the power of 2, that's positive 4. That's positive 4 minus 4. That gives you 0 as well. So when you get a 0 and a 0, that means that it has a point discontinuity. So this means that it has a point discontinuity. And point is just another name for removable discontinuity because it simply has like one little point. So if we were to graph this, we can see that it would go like something like this. And here's your negative 2. I have another one over here. And we can see the point discontinuity right here. Negative 2. So when it's 0 over 0, it has a point discontinuity. When you get 0 over 0, they both have to be equal in order to have a removable discontinuity. They both have to be 0. So you just solve for your x. Well, you just plug in the x that you are given to find the removable discontinuity, to find if it has a removable discontinuity or not, as in this example right here. And again, removable discontinuity is where the function is continuous everywhere except for a hole. I'm gonna jump into jump discontinuity and infinite discontinuity later, but just keep in mind that for it to be a removable discontinuity, both top and bottom have to be equal to 0. Because in infinite, the bottom would be 0, and in jump, you would just have different numbers. For it to be a jump discontinuity, you would have different numbers on both of the equations that you were given. So just remember that. For it to be removable, it has to be both to 0 when you solve for this. And it's continuous everywhere except for a hole. So that's removable discontinuity. Now let's move on to number 10. Number 10 says, explain transformations of the parent function y is equal to ex. Explain right and left shifts, reflections over y and over x, and vertical stretch or shrink and horizontal stretch or shrink. So let's get started. This one, I really didn't really understand it very well, to be honest, because it just gives us the function e of x. So it wanted us to find the right and left shifts, reflections over y and x, and vertical shifts and shrinks and horizontal stretch and shrink, but it just gives us this equation. So if we were to graph this equation, we would get something like so. We'll get something like this. So this, in fact, this is an original. This is the original equation of y equals e to the power of x. So there's really no shifts, no going to the right or the left, no reflections over y and over x, and there's no vertical shrink or stretch or horizontal stretch or shrink, because this is just the original equation. I'm probably working this problem wrong, I'm not sure, but I don't see how else I can work it, because it just gives me the parent function of y equals e to the power of x. So this one really doesn't have anything. So if you're wondering what ex is, it's just simply a big number that just continues going and going and going and going, and that number happens to be that number happens to be 2.7182. So that number just keeps on going, and it's actually really big, and it's all greater than 1. It's all greater than 1. So this one would be greater than 1, so it stimulates growth. And like I said, I'm probably working this problem wrong, but this is just the original function, so we can't really compare it to nothing else. If we were to compare it to its inverse, it would be a whole different story, but that's on a separate question. So we just know that it's greater than 1, so it's growing. So I'm just gonna go ahead and give its domain. Since it's growing, its domain would be negative infinity to positive infinity. Negative infinity to positive infinity. And it would have a horizontal asymptote when y equals 0. But that's pretty much it for this part.